Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will start our discussion about problematic observations in the context of simple linear regression, of course. Let's begin. So, first, it turns out that problematic observations come basically in two flavors. Flavor number one. Maybe the problem is that the value of the predictor variable is too large or too small when you compare it to other predictor values, okay? Flavor number two. Perhaps the problem is that the response variable, the observed response value, say y star, is too far from its predicted value y hat star. Okay? So sometimes these problematic observations have a strong influence on the regression results. Okay? So we would like to start understanding the consequences of having that sort of problematic observations in the context of simple linear regression, and we would also like to develop a detection process. Okay, so as a first step in that direction, right, what we're going to be doing here is illustrating the process of detecting these problematic observations using a graphical approach and some of the quantitative tools that you already have, that you already know, such as hypothesis tests for simple linear regressions. Okay? So, to illustrate the process of detecting these problematic observations, we are going to use an example. Okay? Here goes the example I would like to discuss with you. Okay, it's a small data set. We have 5 observations, 1 predictor variable, 1 response variable, right? And let me say something more about these guys, the predictor variable and the response variable. So x in this case represents the number of hours per week that a student spent studying matrix algebra. Okay? And the response variable that we're measuring is their performance on a final exam about matrix algebra. Okay? Okay. Now, the model that we're going to be considering here is the classical simple linear regression model, right? And by classical, what I mean is this, right? We have yi equals beta 0 plus beta 1 times xi plus epsilon I. The assumptions for epsilon I, same as before. We're assuming that they are normally distributed with mean 0 and variance sigma squared, and that the epsilon i's are independent. And again, by the classic simple linear regression, What I mean is the non-centered one. Okay, this should suffice for this discussion that we're going to have here. Okay, so let's use R to start illustrating this these ideas, this detection process of problematic observations. Let's launch R. As you can imagine, our first step here will be entering the values of our predictor variable and our response variable. Okay, here we go. So x in this case 2, 4, 5, 7, 2. Let's type x. Okay, great. It is what we want. Y equals a vector with first entry 3, second element 4, third, fifth, 5, sorry, comma 6, 7. Okay, so let's see. Great, it is the one we want. Let's fit our model, right? Since here we have our entire data set, let me label this model mod.all. We know that we're going to be using the built-in function lm. We know that the syntax of this function lm is first you need your response variable, then your predictor variable, right? Okay. Now if we want to take a look at the coefficients for this simple linear regression model, all we need is coef and then the name of the model we fit it. Okay, great. So the y-intercept happens to be 4.33 roughly, and the slope, the estimate for the slope, happens to be 0.1666 roughly. Okay, so something else that we can do, right? We know we can do this easily, is how about we carry out hypothesis test. And it's going to be a two-sided hypothesis test. We want to know whether or not we have evidence that beta is 0, that's going to be the null, against the alternative that beta 1, sorry, the slope, that beta 1, that, okay, so here we go, let me rewind. The null hypothesis is that our slope, beta 1, is equal to 0 against the alternative, the two-sided alternative, beta 1 different from 0. So we want to find out whether or not we have statistical evidence to claim that the slope is different from 0, right? Okay, so to do that, one way would be using the summary command, right? We know that that is going to give us a t-test. So here we go. That would be the t-test for the parameter slope. This is the p-value. Since we have a big p-value, we don't have evidence against the null hypothesis. So it seems reasonable that beta 1 is equal to 0. Okay? Okay, I'll be right back. Okay, I'm back. So, let's summarize what we've done so far, right? What we did is including all the observations, right? Including including all observations, what we did is we tested the following pair of hypotheses, H naught against HA, where H naught is that the slope is equal to 0, right, against the alternative that the slope is different from 0, right? And based on the size of our p-value, right, we fail to reject the null hypothesis, right? So let's just write that down. We fail to reject H naught. So we don't have evidence to claim that beta 1 is different from 0, right? So maybe there's no linear relationship. Okay, so how about, right, we supplement this, and we know that it's always a good idea when you're doing a when you're fitting a simple linear regression model to make a scatter plot. So let's supplement this, making a scatter plot. We know that the built-in function plot is going to help you make a scatter plot. That the syntax is first the variable that goes on the horizontal, in this case x, then the one that goes on the vertical, right? PCH is just an option that is telling the plot function that we want solid circles. Call you have used before, so in this case we want blue solid circles. We know that if we want to add the least squares regression line to the existing scatter plot, we can use the AB line function, and then what the AB line function needs is the y-intercept and the slope, and that information is contained in coef, right? We know that when you use that function, then you're going to get as a result the estimate of the y-intercept and the slope. Now let me use LTY. That's an option that is telling the AB line function that we want a dashed line, and in this case I want a dashed red line. Okay, so that's it. So that's what that looks like. Okay, and we know that estimate is 0.166 roughly, remember? So anyway, we don't have statistical evidence to say that that slope is different from 0. Okay, so that's using all the observations. But now what we're going to be doing is see what happens if we exclude the first observation. Okay, so let me remind you what our entire data set looks like. So one way would be just we could retype and do something like x1 equals c brackets, and then exclude the first element of x, and then it would be 4, 5, 7, 2, And then we would do the same with y. We could maybe create another object, another vector called y1, and it would be c equal, y1 equals c brackets 4, 5, 6, 7, and then brackets again. Anyway, instead of doing that, I'm going to show you an alternative. Okay? Maybe some of you already know this. If not, then I think it's a useful trick, if you want to call it that. So let me call model 1 to the model that excludes the first observation. Okay? So model 1 is going to be the linear model, simple linear model, where y is the response variable, but I'm going to exclude minus 1, meaning I'm going to exclude the first observation. And then it would be tilde, right? X square brackets minus 1. By doing that, what I'm doing is excluding the first element of both y and x. Let me show you. Okay? So if we do x square brackets minus 1, then we get rid of the first observation. And if we do the same with y, the result is the same. We get rid of the first observation of y. Okay, so here we go again. Let me retype what I had. Model 1 is the one excluding the first observation for both response and explanatory variable x and y. Okay, so let's find out. Let's see what happened to the coefficients when we exclude the first observation. So now it's this guy, the one we're interested in, model 1. So let me remind you what the coefficients for the entire data set looked like. So we're seeing a significant change in the y-intercept, and there's an important change in the slope as well, right? It goes from positive to negative. Now let's see what happens when we carry out a hypothesis test, right? So again, let's use that summary function, but now we will do that for the model we just created, model 1. Let's take a look. So we have, this is the test statistic, and this guy is the p-value. Again, the p-value is not significant, so we don't have evidence to claim that the slope is, we don't have statistical evidence to claim that the slope is different from 0. So even when we saw this kind of important change, right, when we estimated the coefficients of the model, right, the slope went from positive to negative, and we saw kind of a big difference between the estimate for the y-intercept. Anyway, when you carry out the hypothesis test, the conclusion is basically the same. So maybe it's just due to random fluctuation, random variation. Okay, so now let's do the same thing that we did before. Let's make a scatter plot just to have a graphical idea of what's going on when we exclude the first observation. So let me recycle what we have already done. Now what we want is to remove the first observation. We know that we have this approach, right? Let's remove the first observation just using that idea of the square brackets, then minus the index of the element we want to remove. Okay, so now when we remove the first observation, it looks like this. That's our scatter plot. Now let's add the least squares regression line, but now using the first model, right? So let's use AB line. That's the information that we need, but let me make it look nice. I want a dashed line. I want that dashed line to be red, just like before. And it looks like this. And as we can see, yeah, we have negative slope, right? Okay, but we saw that from a statistical perspective, there is not much difference between the two models, because you know the estimate for the slope is not statistically different from 0. So now that we know our trick to remove observations, let's do the same with the second one. Okay, let me call this guy model number 2, and as you can imagine, we're going to use that to refer to the model that excludes the second observation instead of the first. Let's take a look at what the coefficients look like. Those look more similar to the model with all of them, right? Okay, so just like before, let's carry out a hypothesis test, but now for the estimate, well, for the using the information from the second model, right, for the parameter slope, same parameter, right? Okay, so okay, same conclusion. We don't have statistical evidence to claim that beta 1 is different from 0. Let's do the same that we did before. Let's make a scatter plot, now excluding the second observation. Let's add the least squares regression line. Okay, makes sense. Okay, now let me fit model 3, model 4, and model 5. Okay, so model 3, here we go. We're excluding the third observation. Okay, let me show you the coefficients for that guy. As you can see, those are similar for the model that contains the entire data set. Okay, let's carry out a hypothesis test for that guy. Same as before, right? P-value is big we fail to reject the null hypothesis. Okay, so now let's fit another one, model 4. Let's take a look at the coefficients. Again, we see a change in magnitude for the estimate of the y-intercept, a change in signs for the estimate of the slope. But let's carry out that hypothesis test for this model. Again, big p-value, right? We don't have evidence to claim that the slope is different from 0 based on this on these observations on this data set. So finally, let's see what happens when we exclude the fifth and last observation. Again, a big difference in in magnitudes between the estimates, right, for the model that includes all the observations and this one that excludes the last one. Let's carry out a hypothesis test. Maybe what we're going to see is just like in the other cases, the same statistical conclusion that we fail to reject the null hypothesis, that we don't have statistical evidence to claim that beta 1, the slope, is different from 0 based on the data sets, right? Let's see. Oh my, this is different. It is not just the magnitudes of the estimates, right? The statistical conclusion here is different. We have a very, very small p-value. So if we exclude the fifth observation, we reject the null hypothesis, and moreover, we have very strong evidence against the null. We have evidence that beta 1 is different from 0, right? So let's take a look at the scatter plot. Let's see what's changing here, right? Let me recycle what we had here. Let's exclude the fifth observation. When you see that scatter plot, it seems that a straight line is going to fit rather well. Let's add the least squares regression line from that model. Model 5 is the one that excludes the fifth observation. Really nice, right? Actually, remember that R square measures the variation in y explained by the linear regression. R square represents the proportion of the variation in y explained by our linear model. And guess what? This, right? Summary of model 5 also provides that guy, right? R square. It seems to be very close to 1. So yeah, I mean it makes sense, right? These points are very close to forming a perfect straight line. So it seems that removing that last observation, the fifth observation, that really makes a difference, because we were able to reject the null hypothesis, and when you do that, you have a linear model that fits the remaining data points rather well, right? And again, the statistical conclusions are different, absolutely different. Okay, so let's summarize what we did here together in this video. The effect of observation 5 on the regression results is dramatic, okay? And that is confirmed by looking at our graphs, our scatter plots, and also by carrying out hypothesis tests. So clearly, observation 5 is influential. Let me just mention something else. In the future, in another video, we will talk about a numerical way of measuring influence. We will talk about the leverage of an observation. Okay? Well, that's it for now. Thanks for watching, take care, and keep working hard, please. See you next time. Bye!